Hello everyone, Mrs. Hanson here again. This day we're looking at Chapter 7, taking a start at gases, liquids, and solids. You have your notepad out in front of you, and let's begin. We'll take a peek at the outline, the topics heading our way. We'll look at 3 states of matter. We started our journey in Chapter 1 by saying matter exists as solids, liquids, and gases. Our focus in this chapter is diving in a little deeper into the kinetic molecular theory and discussing the behavior of these 3 states of matter. We'll begin by examining gases. Gases exert a pressure. That pressure we'll define as force per unit area. So as we define pressure, we'll learn that there's 3 different units in order to measure pressure. We'll examine how to convert between those. We'll look at gas laws that relate pressure, volume, and temperature. We call those Charles' law, Boyle's law, and Gay-Lussac's law. We'll re-examine the Avogadro's law and head north on our mole map to the balloon, how to relate molar volume and the mole. The ideal gas law that relates all the variables, PV equals nRT, the ever-popular Pvnert equation, and Dalton's law of partial pressure. All of these, from section 1 through 6, relate to the gaseous phase. We then take a quick peek at intermolecular forces and those attractions between liquid molecules. And the last of our journey, we'll talk about solid state. We'll re-examine heat, those exo and endothermic reactions from our previous chapter, and apply those to how much energy it takes to raise a gram of any object by 1 Celsius degree. And finally, we'll examine some heating and cooling curves and relate that to phase changes. So our journey in this chapter devoted to the 3 states of matter. Much of it, a good half of it, will be devoted to the gas laws. Take a look at this scuba diver. He must carefully plan the depth and the duration of his dive to avoid getting the bends. Have you ever heard of that before? It's that condition, very dangerous, caused from the formation of nitrogen bubbles in the bloodstream. If the diver rises to the surface too quickly, his blood will actually begin to bubble. Here are our learning goals, and I've done a nice job kind of presenting those by sharing the topics. We will measure pressure and convert from one pressure unit to another. That's our first section. We'll describe the relationship of pressure, volume, and temperature of a gas. We describe the relationship between volume and the number of moles. We'll go back and look at the mole map. We'll use the ideal gas equation. That ideal gas equation is PV equals nRT. What do those variables stand for, and how can we solve for that equation? Dalton's law of partial pressure will be examined to find the total pressure of a gas mixture. Liquids exert an intermolecular attraction. We'll talk about dispersion forces, dipole-dipole forces, and hydrogen bonding, and use those to describe such qualities as vapor pressure, viscosity, and surface tension of liquids. And we'll bring conclusion to our chapter by examining solids. What are those things that make solids unique from the other phases of matter, such as the specific heat of a substance and the energy needed to change phase? So with that, let's begin. Those 3 states of matter, gases, liquids, and solids. We know that gases consist of particles that are very far apart from each other, and they move rapidly, independently from one another. They have a very high kinetic energy. And I'm going to just write Ke for kinetic energy. And as you begin to cool gases, gases will form liquids as you remove energy. Removing energy, I remember learning last chapter, is called exothermic. These liquids are more organized than gases, so they're much closer, but they're not nearly as organized as solids. The solids that are packed very tightly together, creating crystalline structures. Very little freedom to move as they're held tight together. Thinking about the kinetic molecular theory, we're being asked to describe the motion of the 3 phases of matter, gases, liquids, and solids. And finally, for you to kind of bring all together into your notepad, you're asked to fill in some of these qualities about gases, liquids, and solids by filling in a chart that compares and contrasts the three states of matter. For example, what about the shape and volume? Well, we know gases expand to fill the entire container, whereas a liquid, it has a fixed volume, but it will take the shape of whatever container you put it in, and a solid, a very definite shape and volume. When we think about the arrangement of particles at the molecular level, gases are very random, very disorganized, chaotic, constant, rapid motion. So they're not very close at all. As a matter of fact, we say gases are mostly empty space. Liquids are still random, but the molecular arrangement is much, much, much closer than that of a liquid, of a gas, but not as close as a solid, very fixed arrangement of those particles. Gases have very low densities. Liquids have higher density, but the highest of all would be a solid phase, very compact solid crystals. The kinetic energy of gases is very fast. The velocity of those molecules are moving very fast. Liquids moderate, and of course solids are extremely slow. In the interaction between gas molecules, well, they ignore one another. There are no interactions, but liquids and solids do have very strong intermolecular forces. So as we compare the molecular action of molecules, here's the same thing visually. Here's a solid silicon dioxide, which is really a major component of sand, a solid. We see that they are solid, are very highly organized and held in fixed positions. A liquid, such as liquid water, are more compacted, but still have the ability to flow past one another. And of course, gases such as nitrogen and oxygen, of course, they have very high kinetic energy and very rapid freedom to move. So think about this molecular attraction as we have very, very high intermolecular attraction for a solid. And by the time you get down to the gases, there's none. There's really no interaction between the particles. They're free to move independently of the other molecules in the same container. There's really nothing to attract them or repel them from one another. Let's dive into the gases first. And we said the vast majority of our chapter will be devoted to gases, a good half of it at least. And we recognize what we called the kinetic molecular theory of gases. Gases move very rapidly. They have constant random motion. So our first assumption of the kinetic molecular theory, and just think about that, kinetic means moving, right? Molecules move. And when they move, they do so with complete random chaotic order. The second assumption of the kinetic theory says that the size of a gas particle is so small compared to the space between the particles. You could say that it is negligible. Think about what that says. If I have a container and it's filled with gas particles, that the size that the gas particles takes up is 0 compared to the size of the container itself. Just so tiny compared to their container. The third assumption of the kinetic theory reads that gas particles exert no attractive forces on each other. No attractive forces means they don't attract or repel. They move independently in random motion. And the fourth assumption of our kinetic theory, as you increase the temperature of a gas particle, the kinetic energy also increases. There's a direct relationship. The direct relationship says if I warm up gas molecules, they're going to move faster. If I cool down gas molecules, they move slower. There's a direct correlation with the kinetic energy, which means the velocity. As I warm and cool, we see the same effect on the motion of a gas particle. And our fifth assumption, When a gas particle collides with one another, they just simply rebound and travel in new directions. There is no net loss of energy. Even though I know anytime two objects collide, there could be a little bit of friction, but this is just an elastic collision. We have talked about the 5 statements of the kinetic molecular theory being used to describe the behavior or the motion of gas particles. Complete freedom to chaotically move within their container. And when a gas particle hits the side of a container, it exerts a pressure. We're going to define the term pressure as a result of collisions with the walls of the container. Every time a gas particle hits the side of the container, it exerts a certain force per unit area. And this is our true definition, in terms of like a physical quantity. Pressure is defined as force per unit area. So you could see if you had more and more and more molecules in the container, it would create more pressure because there would be more collisions. If I just think of equating the term gas pressure to collisions, I can understand the relationship between the number of particles and the temperature, all related to gas pressure. So force per unit area is our definition of pressure. Now, how do we measure pressure? One such device is called a barometer. And this is a picture of a barometer here. If you're standing at sea level, so not high up on a mountaintop where the air is thinner, or not deep down in a valley where the air is thicker, but right at sea level, we have what's called standard pressure. If you're standing at sea level and you happen to have just this like a tub full of mercury, and mercury is a liquid at room temperature, and this is just an open column. And so as the air pushes down on the surface of the mercury, it forces the mercury to rise in this tube. Just like a thermometer works, a barometer works as well. If you have a pressure pushing down on the surface, you can see greater and greater air pressure, you'd have a rise in the column. And the opposite is true. If you have low air pressure, like you would up high on a mountain, you wouldn't have as many air particles pushing down, and you'd see the column drop. A barometer measures atmospheric pressure by the rise and fall of a mercury column. Now notice this right here. If I happen to pull out a ruler stick and I measured the height of the mercury column at standard pressure, it would read 760 millimeters on my ruler stick. And so one of the very common units for pressure is an mmHg, which stands for a millimeter of mercury, reading right off of the barometer's ruler stick, mmHg. And notice that at standard temperature, standard pressure, we have an equivalent value of 760 with a decimal point, meaning that 0 is indeed significant. Standard pressure is 760 mmHgs. When you hear that term standard, it means you're at sea level, and measuring it with standard conditions. Now, another word that we often hear for a millimeter of mercury is a torr. And that's actually short for a physicist named who actually worked with pressure, Torricelli. There's 2 R's in his name, Torricelli. And so we abbreviate torr as a unit of pressure as well. And that's really just an honorary thing for the work that Torricelli did with pressure. Another common unit would be pounds per square inch. Now, not so much in a science lab because we use the metric system, but oftentimes when we're measuring pressure, let's say in a bike tire or a car tire, it's pounds per square inch. And the last unit we'll need to be familiar with is the Pascal. And again, that's actually named after a person. And this is the metric system's unit. The metric system uses pascals. And so since that's kind of a big number, you're more often going to see 101.3 kilopascals as standard pressure. Now when we go to work, we need to be able to convert between these units. And so I wrote down a note here that says you need to commit to memory these values. That 760 is the standard pressure in a millimeter mercury, which is equivalent to saying torr. And that 14.7 pounds per square inch is the same as 760 torr. And that 101.3 kilopascals is the equivalent value in a metric unit. Those all equate to one standard atmosphere. When you see the abbreviation ATM, that stands for atmospheres of pressure. 1 is a number that we assign to 760 millimeters of mercury, the height of a column of mercury at sea level measured with a ruler stick. Do you have those written down? That would be very helpful to put a note there, memorize. And let's model how one of these could actually, how does this employ? Let's suppose we have a scuba diver, typically beginning a dive with a compressed air tank of 3,000 pounds per square inch. And there's a decimal there, so that's significant zeros, pounds per square inch. Convert this value to A, atmospheres, and then B, to millimeters of mercury. So we have two conversions, a letter A and a letter B. Given pounds per square inch, let's find it in atmospheres, and then we'll find it again in a millimeter of mercury. So just as usual, when we start by writing what our unit is that's given. And when I think about a conversion factor, we want over given is our setup so we can cancel units. Well, we want to know in atmosphere, in our first letter A, given a pound per square inch unit. Do you remember from the previous slide that 1 atmosphere is equivalent to 14.7 psi? So this little conversion will simply have us type out on our calculator 3,000 divided by 14.7. And my screen reads 204.0816. And I wrote all those decimals down to remind us we have to consider sig figs. And when I'm using the conversion factor, I had 4 sig figs because this had a decimal with it. So I'm going to ensure that I put down 4 sig figs and report my final answer. Well, what if we started with 3,000 psi, and this time we want over given, our conversion factor, where this time we're targeting millimeters of mercury starting from that psi. Want over given ratio cancels the psi's and brings me to a millimeter mercury. Now remember the benefit of memorizing these numbers. I'll know that standard pressure is 760 mmHgs, and that equates to 14.7 psi's. If I have those memorized, I can easily convert. 3,000 times 760 divided by 14.7. Did you see that key sequence? 3,000 times 760 divided by 14.7, and my screen is 155,102.04, and it has more decimals yet. But remember, we're only allowed 4 sig figs. Now to keep the magnitude the same, 4 sig figs, here's the 4th sig fig, and I really can't use zeros because they'll become trailing. So I'm going to write this as 1.551 times 10 to the 1, 2, 3, 4, 5th power. And that gives me 4 sig figs with the correct magnitude, and my unit would be a millimeter of mercury. That's a big number, isn't it? That's a high pressure. Why don't you try some? I wrote down those conversions for us. You're working to memorize those. Pause the video and just work out these conversion factors just to ensure you're practicing. Come back when you're ready to check. All right, welcome back. We have 3 atmospheres as our given in letter A. We want to know mmHgs. Its conversion is 760 as equivalent to 1 atm. So with letter A, did you just simply say 3 times 760? And when you did that, you found 2280 millimeters of mercury. We had 2 sig figs. That was the number 3, so that's what I said. So we need to make sure that we report that out as well. 2 sig figs means I'll have to report that as 2.3 times 10. 1, 2, 3 spots times 10 to the third. And that gives me the correct magnitude of the number along with scientific notation mmHg. How about letter B? We're given 720 millimeters of mercury. This time we want to know PSIs, so it goes on the top. We want to cancel the millimeter mercury, so it goes on the bottom. We're working to remember that the equivalent values at standard pressure, these are all values for standard pressure, standing at sea level, those are standard conditions. 14.7 psis is equivalent to 760 millimeters of mercury. So we're going to hit 720 times 14.7 divided by 760. And we get an answer that reads 13.926 if I keep going. But I'm looking at, well, look at, there's no decimal point here. So that really is only 2 sig figs. So if I round this, I can get 14 psi and report with 2 sig figs. And how about your letter C? 424 millimeters of mercury. This time we want to convert into the atmosphere given the millimeter mercury. We know the equivalent values, that 1 atmosphere is the same as saying 760 mmHgs. So we simply say 424 divided by 760, and my screen reads 0.55789, and there's even more decimals there. But how many should I report? Well, just 3 sig figs, 0.558 atmospheres. Did you do good? All right, easy enough, converting with pressure units. So let's use these pressure units, kind of an application of, what do we do with pressure? Well, we discuss it as one of the 4 important variables when discussing the behavior of gases. If we want to manipulate the kinetic motion of gas molecules, we can do so by changing pressure, which affects volume. We could change temperature, or we can change the number of particles. Think about that mole as really the measure of the number of particles in a container. We're also going to know that when we talk about temperature, we must always use the Kelvin scale. Always, always, always in this entire chapter. Well, that's not spelled right. And just to remind ourselves, Celsius plus 273 gives us the Kelvin unit. And this is because there is no 0 or no negatives in the Kelvin units, so therefore our math works out, right? We can't use negative or zeros in this algebra, so we'll always convert to the Kelvin unit. Volume and pressure, all 4 of these play a role in discussing the behavior of gases. Now, one at a time, we're going to talk about the following laws. We'll relate pressure and volume in Boyle's law and say they are inversely related. The other part of this statement is saying temperature and moles, the number of particles, are constant. So only allowing 2 of the 4 variables to change, P's and V's, pressure, volume. We'll look at Boyle's law. Charles' law relates temperature and volume, T's and V's, meaning that pressure and moles are held constant. Again, these laws only allow 2 variables to change, holding the other 2 constant. We apply Gay-Lussac's law. Pressure and temperature are directly related. So guess what? You got it. Volume and moles are held constant. And then finally, Avogadro's law. The volume and moles are directly related, and you're holding pressure and temperature constant. And typically we call that STP at standard conditions, standard temperature, standard pressure. Holding those 2 constant at standard values, volume and moles are directly related. And I just want to share with you, you've been staring at this on the mole map. It's finally going north to the land of the balloon as we've been examining our mole map from a previous chapter. So with this, let's dive into each of these one at a time. The first will be Boyle's law. Boyle's law in words: for a fixed amount of gas at constant temperature, the pressure and volume are inversely related. So think about a fixed amount of gas. In other words, I'm not letting in any more molecules, I'm not letting out any more molecules, and I have them in this piston. So just counting 1, 2, 3, 4, 5, 6, 7, 8 molecules in both pictures. The number is the same. The only thing we've done, well, let's also make a note that we're not warming or cooling either in this picture. It's just room temperature, if you will. We push down on the surface of the piston. So we've decreased the volumes from 2 liters to 1 liter. The volume is half as big. Now think about what happens to the pressure. If you only have half as much room to move around, you're going to hit the side of the container twice as often. And so the pressure increased. Notice the first set of conditions. Pressure 1 was 1 atmosphere when the volume was 2 liters. In the second condition, by decreasing the volume from 2 liters to 1 liter, the pressure doubled. PV equal PV for our initial conditions set equal to the new conditions. And this is the expression for Boyle's law. P1V1 equal PV2. Just on a graph, so you can see this inverse relationship. If we put P versus T, as one goes down, the other goes up. That's an inverse relationship. And just think of the compression of a piston. And the opposite would be true as well. If we pushed up on the piston, the pressure would drop. More room to move around, therefore the pressure will drop. So let's try an example of Boyle's law. It reads, if a 4-liter container, now as I read my sentence, every time I trip over a number, I use the unit associated to assign a variable to it. A liter is a volume unit, so I'm going to say the first volume is 4.0 liters. It's containing a helium gas with a pressure of 10 atmospheres. All right, so I tripped over a number and I used the unit to assign a variable. Atmospheres is a unit of pressure, given to me as 10 atmospheres. What pressure? Oh, so I'm being asked, what is P2? What pressure does the gas exert if the volume is increased to 6 liters? Again, I tripped over a new variable. Liters is a volume unit, and it's given to me as 6 liters. We want to know the new pressure. Our Boyle's law says pressure and volume are inversely related. PV equal PV. The first pressure was given as 10 atmospheres. Make sure you are showing your work in your note pack. 10 atmospheres at a volume of 4 liters. What is the new pressure when the volume expanded to 6 liters? Let's solve for P2. Now you can see to isolate this variable, we're going to divide both sides by 6 liters. That cancels the 6 liters and you've isolated P2. So on your calculator, you'll hit 10 times 4, and then you'll divide by 6, just to see the key sequence there for you. Take a moment and hit that on your calculator. Make sure that we get a common answer. 10 times 4 over 6. Whoops, I forgot to turn it on. Darn it. 10 times 4 over 6. And I get 6.67. How many sig figs? Oh, we're only allowed 2 sig figs in our answer, just based on the 4.0 and the 6.0. Those are 2 sig figs, so I'm going to just say that 6.7. And the pressure unit, what we put in comes out, so that's 6.7 atmospheres. How'd you do? How about trying one on your own? Pause the video, work out a Boyle's Law example, and come back when ready. A tank compressed for air for scuba divers contains 8.5 liters. The pressure is 204 atmospheres. What is the new volume if this gas occupies a pressure of 1 atmosphere? Well, that's a significant drop, isn't it? A tank compressed air contains 8.5 liters. There's my V1, and P1 is 204 ATMs. When the pressure drops significantly to 1 atmosphere, we'd like to know the new volume. What volume of air does the gas occupy at 1 atmosphere? To isolate V2, we're going to divide both sides by 1 ATM. This then cancels, and you've isolated the second volume. 204 times 8.5, and this reads 1734, and that would be an atmosphere. We're allowed 2 sig figs based on the pressure and the volume. There's 2 sig figs there. So I'm going to say 1700 atmospheres to report 2 significant digits. Are you ready to check these answers? When you paused your video, did you work ahead? Ready to check all of these? If not, pause, work ahead, and I'll just continue setting these up. We have initial condition of 2 liters, the first pressure at 4 atmospheres. And all that's changing in each of the following conditions, we're looking for the new volume. If we have 5 atmospheres, followed by 2.5 atmospheres, followed by 10 atmospheres, followed by 380 millimeters of mercury. And notice I didn't quite put that in yet, because if I have atmospheres on the left side, I have got to have atmospheres on the right side. You must have like units in your equation or it will fall apart. So the left side of all of these conversions are exactly the same. You had 4 atmospheres in 2 liters. Each time you had a total there, if you just 4 times 2 is 8, and you're going to divide out by each individual atmosphere. So let's do that quickly here. Just to kind of remember, dividing to isolate V2. So in letter A, on my calculator, I hit 4 times 2, divide by 5. And I found 1.6 ATMs with 2 sig figs. 4 times 2, divide by 2.5. And I get 3.2 ATMs. 4 times 2, divide by 10, and we get 0.8. Now I need 2 sig figs, so 0.80 to make sure I have 2 sig figs. Before I can go further here, I have got to find the atmospheres, and so I have to do a conversion where I'm going to divide by 760 using the standard pressure. Now remember, I have to have an atmosphere in both sides or the algebra is inconclusive. So 380 divide by 760, that's 0.50 ATMs. That's what goes right here. I have to have like units. So if I have an atmosphere here, I have to have the same unit over here. 4 times 2, divide by 0.5, and the new volume is 16 2 sig figs, so we're good. Oh, dude, I'm so crazy. These aren't atmospheres. We're solving for volumes. I'm so glad you told me that. I don't know how I just caught that. These are all liters. Thank you for your patience. We're asked to solve volume, so those are all liter units, duh. All right, good work. Well, let's talk about our next gas law. Oh, nope, we have another problem to solve. Did you work ahead on this one as well? This time we're solving for pressure using Boyle's law. Again, give yourself a chance to work these out. Just pause the video and come back when you're ready to check. We have a sample of gas at 15 mils for our first volume, and the pressure is 0.5 atmospheres. What is the new pressure exerted by the gas in atmospheres? So I have to have an ATM there, and if the volume is changed in the following manner. Now notice this is a milliliter, so I need a milliliter on this side as well. So that works. We have a 30 millimeter in the first. In the second, we would have 5 milliliters. In the third, we would have 100 milliliters. And in the fourth, we know that a liter can easily be converted to a milliliter by sliding the decimal over. So the equivalent value is 1,000 milliliters. And each time we have the same left side of the equation, we're just looking to solve for the new pressure. So for instance, in letter A, we'll hit 15 times 0.5 and you'll divide by 30. In letter B, you would hit 15 times 0.5. This time you'll divide by 5. And in letter C, you would hit 15 times 0.5 over 100. And in letter D, when you solved for this, you did 15 times 0.5 over 1,000. And each time there, you're solving for a new volume having like units on both sides. So when we hit 15 times 0.5, you get 7.5. .5 over 30, and this came out to be an answer of 0.25 atmospheres for letter A. 2 sig figs were perfect. 15 times 0.5 divided by 5, 2 sig figs gave me a value of 1.5 atmospheres. 15 times 0.5 this time divided by 100, and we get 0.075, and that's still 2 sig figs, so we're good. And the last one, 15 times 0.5 divided by 1,000, and you get 0.0075. And that also is 2 sig figs. And we've solved for the new pressure when the volume's changed. So Boyle's law, PV equal PV, an inverse relationship. Now let's examine Charles' law. Let's investigate Charles' law. And in words, we're going to write down, for a fixed amount of gas at constant pressure. So those are the two variables being held constant. N, the number of moles, and P for pressure. We're going to compare volume and the Kelvin temperature. We say Kelvin temperature, remember, is always necessary, so we avoid any kind of zeros or negative temperatures in our algebra. Volume and temperature are directly related. That means if I warm up a molecule, the volume will expand. If I cool down a molecule, the volume contracts. They are directly related. The volume versus temperature, if I think about a direct relationship, we see a positive slope. As one goes up, the other goes up. Notice in our first set of conditions, we have a piston again that's free to move because the pressure is being held constant. And remember that the number of particles is held constant as well. So I'm not inviting more molecules in or letting any escape out. At 200 Kelvin units, this fixed number of molecules occupies a volume of 1 liter. That ratio of 1 liter to 200 Kelvin is equivalent to doubling the temperature and allowing that volume to expand. Doubling it, not keeping it the same. Doubling the temperature expanded the volume. So here you see mathematically V1 over T1 is equal to V2 over T2. A direct relationship shows the ratio the same. So Charles' law shows a direct relationship, meaning as I increase the number of Kelvin units, the kinetic energy of the particles increases, the molecules start to move faster and faster and faster, and they spread out. If the temperature goes up, the volume will follow, and vice versa. Remember our formula for converting Kelvin units? Celsius plus 273. So let's try one out. If a balloon, and again, I'm going to recognize every time I have a unit, I'm going to just assign it a variable. So I have 0.50 liters at a temperature of 25 degrees Celsius. And I cool that temperature very cold, negative 196 degrees Celsius. What is the new volume of that balloon? So I'm cooling a balloon significantly. The first volume of 0.50 liters set over the Kelvin unit. So before I put that in, I want to add 273. When you add 25 and 273, the Kelvin unit comes out as 298. Check that on your calculator with me. 298 Kelvin units. That's what goes into the Charles' law value. We're looking for our new volume. And don't forget to add 273 to this Celsius. And that gives me a value of 77 Kelvin units. And remember, always, always, Kelvin. If we had placed a negative temperature, we'd end up with a negative volume, and that makes no sense, does it? So here we have solving for V2. Now, how do we isolate this variable? Well, when we think about isolating the variable, I want you to just cross multiply. So we could simplify the left side first, or you could just cross multiply, whatever you're most comfortable thinking about doing here. And it all just goes back to what you're most comfortable, cross multiply. I'm trying to talk and write. When I cross multiply to solve for V2, I would have 0.50 liters times 77 Kelvin units set over 298 Kelvin units. That's our isolation of V2. Cross multiplying, always start with the side without the variable. So one way to solve for that is to cross multiply, and perhaps that's what's easiest for you. 0.5 times 77 divided by 298. And when I solve for that, the new volume came out to be 0.12919. It could keep going, and that's liters. And let's see, we had 2 sig figs, so I'm going to just make sure I report that as 0.13 liters as our new volume. If perhaps you're more used to solving this in a different way by simplifying the left side, and that's certainly an appropriate thing to do, I just want to represent maybe a couple of different ways, just depending upon your background and the comfort of algebra. You might want to simplify this first, which is totally fine. So if I did 0.5 divided by 298, I get a number, 0.001677, and the screen goes on. Now you can see that you would need to multiply both sides by 77 to cancel this and isolate your variable. So when you did that, you absolutely get the same number. I'm just saying whatever you're most comfortable in doing. I would say don't round until the end. Don't clear your screen until the very end. So if you want to divide first and then multiply, that's way fine. I just cross multiply and then divide. The pathway doesn't matter. Let's try another. Here we have a volume of 0.5 liters and the temperature as 37 degrees Celsius. It's being expelled from the lungs into cold surroundings at 0 degrees Celsius. What is the new volume of the expelled air? So we're just going to remember that anytime we're doing gas law problems, we have to be sure to convert into the Kelvin units. So I'm going to add 273 to both sides. And T1 now will go in as 310. And T2 ends up to be 273 Kelvin units. V1, 0.5 liters, set over T1, 310 Kelvin units, is equal to V2, our variable that we're targeting, when T2 has cooled to 273 Kelvin. Cross multiply to isolate V2. Start with the side without the variable. So 0.5 times 273 Kelvin divided by 310 Kelvin will isolate your V2. You're going to cross multiply, starting with the side without the variable. 0.5 times 273 and just divide by 310. And when you did so, we need 2 sig figs, so I'll report my answer is 0.44. And the unit, well, if we put a liter in, we get a liter right back out. Not too bad. You try a few. Pause your video and work these out and come back when you're ready to try. Remember how important it is not to cheat yourself of the practice. In letter A, we're given 25.0 liters at 45 Kelvin units. We'd like to know the new volume when we significantly warmed to 450 Kelvin units. What does the volume now occupy? Remember to cross multiply the side without the variable first. So to isolate V2, you're going to hit 25.0 liters times your 450 Kelvin units. Then you'll divide that by the 45 Kelvin units to isolate V2. When you hit 25 times 450 and divided by 45, did you find 250 liters? And that's still 2 sig figs. As long as I don't put a decimal point there, we're fine to leave it as 250. How about letter B? We had 50 mils as our first volume, and we had 400, well, not really, That's 673 Kelvin units. Whoops, I had a moment of dyslexia. Hang on. 673 Kelvin units. The T2 is 323 Kelvin units. Let's find the new volume, and if we put a milli in, we'll get a milliliter out as well. So isolating V2, taking our 50 mils, cross multiply the side without the variable. So we're going this direction. V1 times T2 over T1. And we'll solve by hitting 50 times 323, divide by 673. And my screen reads 23.997. We're allowed 2 sig figs, so I'll round that up to say 24 liters. Are you getting these? I bet you are. Let's introduce Gay-Lussac's law, and in this example, this will read for us for a fixed amount of gas at constant volume. So we have a rigid container. The volume is not allowed to change. The pressure of a gas is proportional to its Kelvin temperature. We see a direct relationship. If I place pressure versus temperature in a rigid container, think about a pop can, and don't ever do this, but if you throw a pop can into a fire, into the fire pit at a campsite, run, right? As your pressure begins to increase, and with no way of expanding because of a rigid container, it will just burst. Pressure will increase. So as I warm up a contained volume, pressure will rise, a direct relationship. And just think of this as kind of having a little flame under it. You're warming this piston. The piston, however, is not allowed to expand. It has a rigid container. When it doesn't expand and I warm it up, the pressure is going to increase. So constant volume, pressure will double when the temperature doubles. So this is a P1 over T1 set equal to P2 over T2. And remember, this has to also always be in a Kelvin temperature. What's being held constant? Constant volume, constant number of particles. Let's try one. The tire in a bicycle is cooled in a garage, and it's at 18 degrees Celsius, and the pressure is given to us as 80 pounds per square inch. What is the pressure? After riding the bike, the tire warms up when you ride it, and it warmed up to 43 degrees Celsius. What would the new pressure be? Well, before I go on, I want to make sure that I remember to convert into Kelvin. So my 18 Celsius converted to Kelvin units is actually 291 Kelvin units. And 43 converted into Kelvin gives me 316 Kelvin units. So my 80 psi set over the first temperature of 298 Kelvin will be equal to the new pressure we're solving for, set over the 316 Kelvin units. Now we warmed it up. I expect the pressure to increase. As I warm up a gas and it's not allowed to expand in its container, the pressure will rise. Remember, cross multiply the side without the variable first. So 80 pounds per square inch times 316 Kelvin units divided by the 298 Kelvin units, that's our T1, isolates P2. I'll hit 80 times 316, divide by 298, and we have 84.832. Now how many sig figs? It looks like we're allowed 2. So I'm going to round to 85 pounds per square inch. You try one. Read about a pressure cooker, pausing the video, work this problem out, and then come back to me. These are quite popular right now, aren't they? Pressure cookers. By heating the contents of a pressure cooker at constant volume, the pressure increases. If the steam inside is initially at 100 Celsius, at a pressure of standard unit 1.0 atmosphere, what is the final temperature if the steam increased the pressure to 1.05 atmosphere? Oh, so the pressure went up a little from 1 to 1.05 atmosphere. So what happened to the temperature? Well, I know it's going to go up, but I also remember that I have to be sure that I put this into Kelvin units before I can set up any kind of math problem. And remember, that means that when we get our answer, it will come out in a Kelvin unit. So let's set up P1 over T1 equal P2 over T2. Now remember, that happens to be the target variable. I still want you to employ the same type of algebra. I want you to cross multiply, but this means you're going to start with the side without the variable. This is this direction, isn't it? When we cross multiply, we start with saying 373 Kelvin times 1.05 atmospheres. That will be set over 1.0 atmospheres, and that isolates T2. So cross multiply the sides, the two numbers, without the variable and divide by the third number. Let's hit that. 373 times 1.05, divide by 1. Now when we get this answer, 391.65, that's my Kelvin unit. To go back to the Celsius answer, subtract 273, and we get 118.65 degrees Celsius, but we're only allowed, looks like 3 sig figs, so I'll put that as 119 degrees Celsius. You must always have a Kelvin unit. And so if you have a Kelvin unit, it comes out as a Kelvin. If you're asked to convert back to Celsius, do so by getting rid of the 273 at the end. But you cannot take a shortcut. You cannot put 100 into this equation and expect a right answer. It will not work. How about trying these on your own? We have a temperature, 0.5 liters of a gas, 25 degrees Celsius, and the pressure is 1 atmosphere. Oops. The temperature of a 0.5 liter gas system at 25 Celsius and 1 atmosphere is changed to each of the following temperatures. What is the final temperature? What is the final pressure? So we're being asked for P2 in this example, and we're just changing the volumes or changing the temperatures one at a time. This really is a fixed value. It's a distractor in the problem. It doesn't get used, right? It's a fixed volume. We'll never use 0.5. It's just there to tell you the size of the sample. And some of us might get tripped up thinking we better use it in the problem, but we don't. Here is T1. Here is P1. Here is T2. We're looking for P2. So each time we set up the equation, we have the same left side, 1.00 atmospheres set over 298 Kelvin units. That's our T1. So each time we're going to have the same left side. We'd like to know the new pressure. And look, they've given us the Kelvin units. How nice. So again, 1.00 atmospheres over 298 Kelvin. We're going to pull out P2, and this time the temperature went to 150 Kelvin. 1.00 atmospheres set over 298 Kelvin. Looking for P2. (50 plus 273 is 323 Kelvin units. And letter D, 1 atmosphere over 298 Kelvin units set over, what's this guy? And that's 473 Kelvin units. There, we got them all set up. Is that matching what you have on your page? Now we're just going to cross multiply 1.0 times 310 divided by 298. Cross multiply 1 times 310 divided by 298. And I'm finding, what do we need? 2 sig figs. So I'll do 1.0. And that unit comes out as an ATM. My screen reads 1.04, but I'm going to round to just 2 sig figs. So again, cross multiply the two numbers without the variable. 1 times 150 divide by 298. And we need 2 sig figs, so I'm going to write this as 0.50 ATMs. Are those matching? 1 times 323 divide by 298. 2 sig figs, so 1.1 ATMs. And the last one, 1 times 473 over 298. And that comes out to 1.6 ATMs, all cross multiplying, remembering always, always to have the Kelvin units. And let's pause here. We'll take a break from our lessons. Come back to me when ready. We're going to talk about the combined gas law with some examples next.